Hello, everyone. Welcome to Lightning Talks number 4. The theme is Tools for Open Science. We've got 4 speakers. They're each going to speak for hopefully maximum 7 minutes, ideally a bit less than that, so we've got time for questions. First up is Robert Turnbull. Robert is the Research Data Specialist at the University Data Analytics Program, and so is Mar, and I've been told Mar can stay on stage basically the whole time.
Just get you guys in here so that the folks.
Cool. Hi everyone, my name is Mar and I'm here with Rob. We're both research data specialists at the Melbourne Data Analytics Platform, and we're here to talk to you today about Crunch, which is a data processing orchestration tool for open science. And I just want to acknowledge that our colleague Simon also has been helping us with this project. So the motivation for this piece of software that we've developed is a collaboration that came in from the School of Biosciences, Associate Professor Berg-Bruggen, and he wanted to basically download every single publicly available metagenomic data set that contained a water element to it, and develop a workflow for the analysis of this and be able to find microbial eukaryotes that maybe weren't sequenced before. So this was the dream team assembled to work on this. So Bobby is a bioinformatician, an expert in this. My background is in mathematics and neuroscience. Rob is mathematics, but also digital humanities. And Ed works in astronomy and astrophysics. So we wanted to build a workflow for this project because so that the same workflow could be run on all of the data sets. And so this helps for reproducibility, making sure that you're doing exactly the same data analysis processing for each of the data sets. And so they're all comparable between each other. So Bobby had been working on something already very similar. And so we basically had the bioinformatics problem solved. But the next problem was the data for this project. Haroon was interested in 670 studies with public metagenomic data that had been uploaded to the European Nucleotide Archive, collected using Illumina and containing paired and reads. And the size of the raw files for each study ranged from small ones, 30 megabytes, up to 4 terabytes. And so in total, there were 90 terabytes of data to be downloaded and processed. Of course, we were using the university's high performance computing system, which is called Spartan, and that doesn't have anywhere near that kind of storage. The maximum storage you can get is about 5 terabytes. And so we were faced with the problem of having to download all of this data, store it somewhere safe, copy the data over to Spartan for compute, setting up the workflow for that data, and the workflow for each data set has specific parameters, like which resources you're going to need and other parameters that were set up in a JSON file, run the workflow. Of course, there's limited storage on compute. So we needed to run it and basically delete everything again as soon as it was run. But what happens if it fails? How do you know where it failed, which part you need to pick up and run it up again, and then upload the process results for it and make them available. And we needed to be able to do all of this with pretty minimal manual intervention because there were 762 samples after splitting in batches of no more than 280 gigabytes. And so this is where Rob's expertise with Django comes in, and he'll talk to you about the solution we came up with.
Sure. So we came up with a piece of software called Crunch. So Crunch is what we call a general purpose data crunching orchestration tool. So it has 3 components. The first is that there's a web application that uses that in the cloud. This is written in Django, which uses Python. It's a web framework for building database-driven websites. The website allows users to create what we call data sets, and each data set corresponds to a collection of files and metadata, which is designed to be run through a workflow. Each data set has its own page on the website with which displays all the information about it. The second component is the data storage. As Mar said, you often can't fit all the data you want to process on the place where you're doing the compute. And so we're using, you could use any type of data storage that you want. So anything that works that's compatible with Django. So you could use Amazon S3 or just FTP or Google Cloud. We wrote a plugin to work with the University of Melbourne's data storage infrastructure MediaFlux. And you can write your own plugins for any kind of storage that you want to use, anything that works with Django's API. And the third component is the client that runs on the place where you're doing the compute. So that could be a high performance computing system It could be on a cloud VM, a virtual machine, or it could just be on your laptop, wherever you're doing the compute. And this the client that's part of Crunch first, or you run the client in the command line. So you could say Crunch loop. So it just continually loops through all the different data sets, downloads the data set from storage, runs the workflow that you define, and then copies everything back to the data storage and updates the server for each the web app each time it does a step with all the kind of diagnostic information you need, and tells so you can see on the website where things are up to, and be able to troubleshoot when problems come. So we'll just hit 5 minutes, and all the resulting files are available to be downloaded from the website, and you can set the permissions so you can restrict it to your team, or you can make it open to the public if you want to use the website to allow the general public access to your results. The Crunch is an open source tool available in an alpha release on GitHub, and if you're interested in finding out more, come chat to us afterwards. Thanks very much.
Excellent. Next up is Aaron Wilcox. Aaron is a research associate on the Replicats project, part of the MetaMel research group at the University of Melbourne. Aaron.
Yeah. Right. DevOps to ResOps, implementing DevOps components to improve computational reproducibility. Let's begin. So, computational reproducibility across scientific disciplines is varied, with calls for initiatives to include data, code, and workflows. Reforms have seen open access initiatives increase data sharing policies across scientific disciplines. However, these initiatives are only partially successful. We have seen an increase in data availability statements, checklists, and guidelines, but enforcement of such the policies from publishers is at best moderate, as the standards and strengths of these policies vary across disciplines. Researchers are not sharing the rich historical provenance that modern technology affords, only the published results. Exploring factors that limit reproducibility, include lacking detailed documentation or clear annotation of methodology, unable to obtain data or code, latest version of the code, or lack of details of workflow, and lack of computational environmental system dependencies. So the environment, versioning, documentation, workflow, competition, data, and code are all important components of reproducibility. They are all each components that together play an essential role in modern research. When implemented into a workflow, they could help to effectively communicate science. However, little forethought is given to structuring a computational workflow, as researchers lack formal training in software development practices. The reasons reproducibility reform fails is the system favours quantity over quality, and there is little consensus on what reproducibility looks like in practice. Researchers don't see value in implementing open science practices due to a lack of incentives for transparent workflows, as there is little or no acknowledgement of their time and effort. At the institutional level, inconsistent policies, interventions, training, and data management plans have had minimal impact on increasing reproducibility, as they take place too late in their career, or fail to take into account incentives such as recognising software as an output of research. At the individual level, researchers are seldom exposed to adequate programming practices and dedicate valuable time self-teaching software engineering tools without any formal training in computational methodology. As such, authors are often unwilling to comply to data and code sharing requests, or are generally reluctant to publish their code. So researchers are required to integrate data and code into a workflow that is reproducible using modern computational tools and processes without recognising their additional time and effort. There is a misaligned culture between the criteria for reproducibility and the expected methodology in which researchers work. We need to look at the solutions that are being accessed from the scientific community and the tools and processes that are fostering open science. A number of communities have attempted to implement technical solutions guided by the FAIR data principles. For example, the FAIR for research software extends the FAIR principles by treating code and data as research objects. This has a couple of important implications for science, as it A, values the convergence of best practices from the scientific community, and B, recognises the guidelines, tools, schemas, and repositories as a shared resource. Additionally, it directs us to explore how these are being integrated into modern scientific workflows and how they are changing the way in which we collaborate and communicate science. A solution to manage data pipelines is to create a scientific workflow. Scientific workflows provide a formal specification of the scientific cycle from the data collection analysis through to publication. They bridge the gap between the technical and the human processes, capturing a rich provenance information for researchers throughout their investigations to allow the execution of such data flow. Computational skills are now an established part of the researcher's toolkit, irrespective of their research discipline. Workflows including container technology, automation, and version control are well utilised across scientific disciplines, improving scientific collaboration and communication, replicability, and transparency. These are not, however, a unification of any specific technologies and do require additional training and education, which, as mentioned earlier, researchers undertake themselves. And to DevOps. DevOps is a cultural movement and a technical solution that shifts the way individuals think about their workflow and is a fundamental characteristic of software development that interacts between development and operations that values technical diversity. DevOps improves collaboration and stakeholder communication through a systematic way to incorporate components and maintain system configuration. It's centered around the idea of collaboration by bringing people together to align to organizational incentives. The tools are usually open source, implement some form of version control, automation, continuous practices, and container technology. The roles of the scientists differ to that of DevOps, and that scientists are generally developers, testers, and operators condensed into one role. And to distinguish computational reproducibility to that of DevOps and identify the best practices and tools within the scientific community, the term ResOps, coined by DeBaser in 2015, is used. If computational reproducibility is the ability to reproduce the same outcomes from the same data and code and software as the original study, then the criteria for reproducibility should be the formal specification of a scientific workflow, implementing community best practices that align with open science incentives. We create software. In essence, and by using DevOps components in the scientific workflow, we realign the culture using community-led best practices. So to conclude, there is a systematic gap between the creation and sharing of scientific knowledge, and that the reproducibility crisis narrative is unhelpful, as it implies that the culture of science is in a situation that cannot be resolved. It is, however, a call to action and one that underpins the open science community. And to quote Stevenson in 2022, transparency acts as a quality control mechanism which incentivizes authors to publish results that are more robust and allows others to reproduce analysis. Then the criteria for such quality should be set by the implementation of a community-enabled practices that incentivizes computational reproducibility. Thank you.
All right. Our next spike of lightning comes from Nick here. Nick is a director of the Melbourne Data Analytics Program and an associate professor with the School of Computing and Information Systems at the University of Melbourne.
Thank you very much. And I've got my secret weapon here, Mark, who talks really fast. So we'll get an 8-minute talk into the 5 minutes. Really, this is just a brief advertisement for the Melbourne Data Analytics platform. I guess it's a University of Melbourne initiative for supporting data-intensive research across the university. For those of you who came to the discussion session that we held yesterday, you're going to have seen some of this before, apologies, but we'll be quick. And really what I want to do is outline a particular institutional model for increasing digital literacy across the university and hence improving the quality of the research that's conducted. And we've just heard really good examples of the technical skills that are widespread across a whole bunch of research disciplines at the moment. And what we want to do by engaging more broadly is sort of raise the profile of Mdap both within the university but also more broadly across the national research landscape. I think there's a lot of opportunities here that are remain to be tapped. So what is Mdap? Mdap is basically a team of about 19 research data specialists who are employed to enable data-intensive and compute-intensive research across all disciplines at the university. We collaborate with every single faculty from fine arts and music through to law, through to social sciences, through to STEM and medicine. It was formed about 4 or 5 years ago when the university was undertaking a program of work called the Petascale Campus Initiative, which was looking to upgrade the university's computing infrastructure to accelerate the transition towards data-intensive research across the university campus. And now a lot of that was focused around the physical infrastructure required for computing, but there was recognition that there was also a need for a workforce who was able to ensure that that computing facility that was provided was accessible not just to the the disciplines that traditionally made use of computing infrastructure, but generally across the entire university. And hence the idea of an on-ramp, a digital on-ramp was born, and that became Mdap. In parallel with this, there was also a recognition that the researchers who work in that type of digital research support traditionally sort of lived in a fairly insecure type of employment situation. And so a parallel sort of aim of Mdap has been to try and create and navigate sort of the new models of workforce to provide secure employment and secure career pathways for people who are working in research support. Okay, so over the next 4 years, which is sort of how long Mdap has existed for now, it's completed approximately 50 major projects in collaboration with all of the faculties. This just gives a sort of a taste of some of the different topics that those projects have been in, kind of illustrating, I guess, the breadth of different disciplines across which the Mdap team have worked. I'll hand over to Ma now to talk about some of the different modes of. Well, why doesn't the down button work anymore?
Oh, because clicked. That's all right. Yeah. So this is the context in which Mdap was established, thinking about these different levels of support for data intensive research. At the bottom, we have learning basic digital skills, like learning how to program in Python or how to program in R or how to use Git or things like that. So digital capability training, and then going step by step towards being able to apply to competitively funded projects that use digital skills. And so as you go up the pyramid, it's increasing the research impact, but also increasing the researcher independence. So how do we get as many researchers as possible from that bottom of the pyramid up to the top is the model. And so in Mdap, when it was established, we started working on that top of the pyramid. And so that's been the main thing that we've worked on, which is collaborations, funded engagements, and short projects, always in collaboration with researchers from many of the 10 faculties, where they bring the research, the domain expertise, the research question, usually the data sometimes, but not always. And we provide the technical expertise to be able to move this project forward. About 2 years ago during COVID, the digital skills training team within the university was incorporated into Mdap as well. So this is the team that delivers introduction to Python, introduction to R, LaTeX, etc. So these introductory courses to digital skills that are needed to get to the top of the pyramid. Then we realized that there's a gap in the middle that nobody at the university is really covering. And is not that big of a problem in disciplines like STEM, because maybe a lot of the people that are around you or your colleagues already have these skills. And so when you graduate from introduction to programming in R, there's still a big gap between that and being able to actually use R for your research with your data, with your research question. And so recognizing that the greatest need for this kind of support is in the humanities, arts, and social sciences, we created the HAS task force, whose objective is to identify small groups of researchers in the humanities, arts, and social sciences who have similar needs, and be able to deliver small workshops. And so Mdap, these are the different types of collaborations that we run on. So we do faculty supported collaborations, which we do an annual call, and their collaborations lasting between 3 and 9 months. And they get selected by a independent committee of senior researchers. We can also do research funded engagements where you can second an individual Mdap member or engage a team of data specialists. We also do advice and short projects. So that's been the bulk of our work in the last 4 years. Digital skills training is all the regulars. And we have 3 really skilled trainers who deliver all these programs. And then the HAS task force was established in collaboration with the Digital Studio, which is within the Faculty of Arts. And I already explained actually what that is. So I'll go back to Nick.
Okay, so that's been a really very brief overview of a lot of complex activity that Mdap is involved in and is undertaking. But I guess this was just intended as I say, to raise awareness and to sort of be a touch point for further conversation. For local researchers at the University of Melbourne, if this sort of sounds interesting and you weren't previously aware of this, please do get in touch for more information about how to engage with us. But also particularly for researchers outside of the University of Melbourne, we're really interested now that we have learned a lot of lessons, made a lot of mistakes, sort of improved a lot of processes locally to start or to continue engaging beyond the University of Melbourne to talk to others who may have similar platforms at other institutions or are looking to try and advocate for or establish similar platforms at other institutions. It's not an easy pathway, and we have been very, very lucky. We're aware of that at the University of Melbourne to have had this opportunity. But I think it does give us that ability to gain lots of experience in scaling up this type of research support work and starting to address some of those challenges associated with career pathways and advancing recognition of team-based research. And I'll stop now because I've just noticed Adrian stand up. So thank you very much, everyone.
Thank you, Nick. Very jealous of that. So our last speaker is online. It's Alexandra Davidson, and she's currently completing a PhD at Bond University, and we're going to do a recording, but Alexandra is around as well.
My name is Ali Davidson. I'm a research assistant at the Institute for Evidence-Based Healthcare, and today we'll be presenting on a project I've been working on with an amazing research team titled Taxonomy of Interventions at Academic Institutions to Improve Research Quality. Research waste is a key issue for many research institutions, and we know that 85% of research is wasted due to poor research design, non-publication of research, and a lack of dissemination, and poor reporting. These all lead to low research reproducibility and replicability, which are key criteria to ensure that research is robust and of high quality. So what might research institutions do to address this issue? To answer this question, we developed a taxonomy to help classify interventions to reduce research waste. To identify and classify interventions, we developed a taxonomy. We first used an exemplar paper that developed a taxonomy of interventions at the journal level, whereas we focused on the institutional level. We then used Mickey's behaviour change wheel to identify further classifications and sub-classifications of the taxonomy. Alongside this, we also conducted a literature search to identify peer-reviewed literature that described or evaluated institutional level interventions to improve research quality. The draft taxonomy was then piloted at last year's AIMOS conference, and we sought feedback from workshop attendees. And finally, cycles of drafting and revision from the research team, who come from a variety of discipline backgrounds and levels of research experience. So let's get into the taxonomy. I blanked out the text from most of the taxonomy to improve readability. First, I would like to draw your attention to the top few rows of the table, which outlines the stage of research the intervention is being conducted. This includes whole of institution interventions, where an intervention may not fit into a specific research stage or may cross over several stages, and before study conduct, during, or after. Now, to outline the different shading in the taxonomy, the dark grey cells represent interventions that had peer review literature of the intervention. The light grey cells represent interventions where we did not identify peer review literature, and the cells that are white represent cells that we did not identify current interventions. This does not mean that they do not exist. It just means that throughout each stage of the taxonomy development, an example was not identified through brainstorming or the literature search. And these blank cells represent potential gaps in the literature that could be explored for future research. I now would like to draw your attention to the far left columns. The dark green column is the underlying mechanisms of intervention, including the institutional culture and individual ethos around research reproducibility and replicability and overall practices. Because prioritization both at the institutional and individual level to ensure we have quality research practices is vital, and this influences how well the interventions are applied and accepted by researchers. Then we have the type of intervention, and this includes research tools, education and training, incentives, modelling and mentoring, review and feedback, expert involvement, and policies and procedures. These were also matched to Mickey's behaviour change wheel, which are outlined in brackets. We know that in order to implement interventions and ensure they are sustainable, it really boils down to research behaviour. And just as an example in the whole of institutional tool intervention, availability of open source and reproducible software packages. We're having software packages available for researchers to then openly share and use. This slide is the condensed version of the taxonomy, where we selected prime examples from each of the cells where available. This will sit in text of the publication, which is in final drafting stages, and the full taxonomy with about 93 different interventions will be an online supplementary material. Have a look at the taxonomy. What row has the most blank cells? The incentives row. So what can research institutions take away from the taxonomy? I'd like to highlight the lack of interventions in the incentives row. We all know that research funding is tight and grants are becoming few and further between. And in order to sustain research practices that are of high quality and focusing on reducing research waste, we need adequate and appropriate resources. Evaluation of interventions for their impact on reproducibility and replicability. We acknowledge that we only identified 11 peer-reviewed articles that had intervention evaluation. We encourage the implementation of interventions that are no or low cost and high benefit to the institution, including making researchers aware of current resources and tools, such as software that they already have licensing for, to look inward at their own research culture and identify whether this needs to be addressed, encouraging mentor-mentee relationships, and especially highlighting how both parties can benefit from formal and informal mentoring. Thank you. I'm open to any questions or feedback, so please do not hesitate to email me.
Thank you, everyone. That is perfectly at half an hour, or it will be by the time I finish this sentence. So I think any questions for Nick, Aaron, Mar, Alex, Robert, see them in the next break or early tomorrow morning. And then we're on to the school project now.